Hello, welcome to this technical webinar to learn about semiconductor chip design and manufacturing and career opportunities in this industry. This webinar is brought to you by two BUET alumni organizations. Both happen to be in North America. If you are wondering who they are, here is a brief introduction. BUETian 89 Foundation of North America is an organization consisting of BUET alumni, mostly from the HSC 89 batch. This organization focuses on various charitable projects in Bangladesh and abroad to help empowering unprivileged communities. BUETANA, on the other hand, is open to all BUET alumni residing in North America. This organization focuses on promoting interactions among BUET alumni and their friends through professional activities and networking. So if you are a BUET alumni anywhere in the North America, please join BUETANA ASAP. If you are interested in learning more about these nonprofit organizations, please visit their websites, which will be posted in the chat shortly. Now back to the seminar. This session is divided into two segments. During the first segment, we will learn about semiconductor chip design and manufacturing, as well as career opportunities in that area. In the second segment, our expert panelists will answer your questions from both Facebook Live and Zoom chat. So if you have any questions during the first segment, which is the presentation segment, please post them in the Zoom chat or Facebook Live comments. And with that, I would like to invite our good friend and a subject matter expert in semiconductor area, Manjur Hussain, to start the presentation.
All right, thank you, Shahnaza Proznipa. Hello, everyone. This is Manjur Hussain sitting in Phoenix, Arizona. I welcome you all. Thank you for joining in. Good morning, good night in Bangladesh and wherever you are joining. Let me start the presentation topics. Let me share it. Hopefully you are able to see it, everybody. So yes. Today we are going to talk about semiconductor chip design and the fabrication part. This is a high-level overview, and then we will also discuss career opportunities, whatever available in these fields. Along with me today, we have Ashfaq Ansari, who is a senior Intel engineer working in a manufacturing site. Then we have three other guests as a expert panel for Q&A session. Mohidjaman Mahmoud Konak, he is an expert in industry. He works at NXP currently as a business operation manager. Then we have Jawadat Rahman Rumal, which is also an expert in his own area, platform validation architect, working at Intel for a decade, almost 2 decades. And then we have Jubaid Islam Mithu, who is a senior analog engineer working at Intel Corporation, also a Intel veteran working for more than 2 decades. Moving on to our table of contents. Today, as you can see, you have 3 segments from the presentation side. First segment is talking about the semiconductor chip design phase, design technology. And on that category, we have what is the semiconductor in a very classical definition and why it is so important. Semiconductor chip design flow cycle. We'll look at the fundamentals of semiconductor design, and then we'll look at one of the design technology, which is VLSI, and why VLSI design is so popular. Then we'll talk about the transistor integration level in the integrated circuits. There is a Moore's law related to this transistor integration level. We'll touch upon on that. And then semiconductor process technology. What is process technology and what is the importance of it? So that is the first part of design related. And then the second part, we'll talk about the semiconductor or chip fabrication. How chips are made in the fab. What are the different fabrication steps? We will touch up on that, and there will be a video segment. In the third segment of this presentation, we will talk about the career in this design and fabrication field. what is the semiconductor chip demand at this point? What is the job market look like in the USA and also in globally in the semiconductor industry, the job market? What is the career path and opportunities available? Job types, job functions, how does that look like? What are the soft skills, qualifications, and you need to build a career on that side? And lastly, you will also have a one slide for some suggested coursework and other knowledge for some specific degree people. So with that, I'll move into the real content on the semiconductor design technology. By the way, all of your question, hold on for now. As we said in the beginning, there will be a dedicated question and answer session at the end of this presentation, and you will get a chance to ask question. And to ask question is to type your question in the Zoom chat, and whoever in the Facebook, you type your question there. We will try to collect from there. So what is a semiconductor? In the classical definition or in the textbook definition, those who are in the school, you know, semiconductor means a material that has a electrical conductivity less than a conductor but greater than an insulator. It lies in between. It is not a conductor or it is not insulator. It is in between. So that's why it is semiconductor. So as you see in the picture, aluminum, copper, gold, iron, silver, those are very good conductor materials. In the right hand side, diamond, glass, oil, plastic, rubber, those are the example of insulator. So they don't conduct electricity at all. But in the left side, they are very good conductor. But in the middle, you see germanium, selenium, silicon. These materials has electrical conductivity, not so good conductor, and also it is not completely insulator. It is in between. So that is a good for semiconductor chip designing. So in the chip industry, when we say semiconductor, we do not mean this material. We do not mean this germanium, selenium, or silicon. We mean chips or IC. So throughout this presentation, whenever we say semiconductor from now on, we will mean it is an IC or it is a chip. Okay. So as you can see in the picture in the bottom one, all this black, black box with the pin, those are chips. You see, I see it in the top 1, 2, 3. Let me bring my. Okay, so as you can see here, this is a chip, this is a semiconductor in industrial language. This is semiconductor. This, right? So that's what we mean when we say semiconductor in the chip industry. We usually mean the IC. We don't mean those germanium silicon material. Okay. So now, why semiconductors are so important? Why we talk about so much? Well, as you can see, it is in everywhere, right? In the communication industry, in the computing industry, consumer or IoT industry, healthcare, smart energy, transportation. Where is not, right? In the communication industry, you see radios, smartphones, televisions, watches, everything. It is driven by the semiconductor. It has the chips, right? Computing industry, all of your computer, laptop, wireless, HD everything has its own chip driven by the semiconductor. Consumer electronics, smoke detector, refrigerator, washing machine, everything. So I can go on and on from this example. So these semiconductors are the foundation of the modern technology. Billions of connected devices on this planet would not function without them. Semiconductors power almost everything in our daily lives, from smartphones to planes. Semiconductors evolved to improve technologies, and they do wonders for our entertainment and convenience as well. Also, semiconductors have driven advances in communications, computing, healthcare, military systems, transportation systems, clean energy, and many other countless other applications. They are giving rise to a new technology now, for example, AI, artificial intelligence, VR, virtual reality, IoT, energy efficient sensing, automated devices, robotics, which hold the promise to transform society for the better, right? All these devices are powered by semiconductors, which improves our lives, increase productivity, and drive all level of economic growth. So that's why semiconductors are so important. You cannot imagine without semiconductor today, right? All right, so moving into the chip designing, semiconductor designing discussion, we'll look at it how we design this chip. You know, you may wonder the worldly engineer knows, but we're trying to give you a very simple flavor how we design those semiconductor or chip. So in this chip design flow or cycle, as you can see in the flow diagram, to develop any or design any chip, at the very first, some idea came into the designer's mind. Okay, I'm going to bring this kind of chip into the market. And then he developed some specification of that chip, meaning what it will do, what kind of power it will consume. From this, once you have the spec developed for your intended chip, then you write architecture, and in RTL, there are a set of engineers who write architecture and RTL for that chip in a language. And then you go to verification. In number 6, you see the synthesize. It is a part that convert your RTL code into a design in your computer. Once you are done with this, you are happy that yes, this is my chip. Then you send this chip to foundry, number 7, right? It is the fab. That's where you up until number 6 is your design in the computer. After that, this design goes into the fab. In the foundry, it becomes chips, and finally you do a packaging. Last part is packaging. You close the chip with some coverage to protect from damage. So in a very simple flow diagram, this is how engineers, researchers, and technicians they design the chip. From 1 to 6 is design phase, 7 to 8 is your fabrication phase. I have a detail of this slide next. We will go into there. Here I'm just giving you just a pictorial situation scenario. Okay. So what is the fundamental unit that chip has? The basic building block of any chip is the transistor. What it is transistor acts in the chip, it acts as a switch in the digital chip, meaning it turns on and off, so it becomes 0 and 1, and those digital computer or digital circuit understood 0 and 1, and then it works accordingly. So in a very simple term, a chip is built of transistor. Transistor work as a switch, 0 and 1, and with all the 0 and 1, all whole work of the world has been done, because computer understands 0 and 1, nothing else. So computer got an instruction by 0 and 1. So in the middle of the slide, you see what is transistor? Well, it is electrical symbol is like this, 3 terminal, GDS, we call ground, gate, drain, and source. And the real world picture in the market, you will see this 3 terminal device, that is transistor. In the right hand side, this is a 3-dimensional picture of the transistor in the fab. That's how fab create this transistor. Only one thing keep in mind here is that, so this is your gate terminal that we saw in the first picture, G, source terminal, S, and D terminal, drain. So transistor is a 3-terminal device. Just keep one thing here, not much. The L, if you see the L and the W, length, gate length of the transistor and width of the transistor. These 2 parameters will show you later on why I'm indicating here. Okay, so just a simple note, transistor is the basic building block of chip, and this is the transistor. Now there is another part, just keep it as a note, is the logic gates. So logic gates are built by this transistor. They perform logical function, meaning digital logic gates are combined to make digital logic circuits. Logic circuits means circuits that perform adder, subtractor, multiplier, comparator. This kind of function can be done by the logic circuit, and digital circuits are the backbone of digital IC. So basically, transistor, remember one name, very important. Logic gates, another important thing for the digital design domain. Okay, so keep these 2 terms in mind, transistor and logic gate. Okay, now in this slide, we'll look at it, the semiconductor or chip design technology. One of the design technology that we will talk about today is the VLSI. What is VLSI? It stands for very large scale integration. Very large integration of what? Very large integration of that transistor that I just showed you in the previous page, right? So VLSI is the process of creating an IC by combining those transistors that I showed you. We combine those transistors in a million to create an IC. Okay. Because we scale or integrate a lot of transistors, that's what we call very large scale integration of transistor. So VLSI is a modern chip design technology which defines the integration level of those transistors in one chip, in a single chip. While this technology is not new, it started in 1970s, in the 70s era, right? And this technology is used mainly for microprocessor design, memory design, and microcontroller design, and many other electronics. Okay. So that is VLSI, right? Very large level scale integration of the transistor to build chip. Now, why VLSI design is so popular? What is the motivation of using this technology? Because if you develop a chip by integrating lot of transistor into one chip, you get a PPA benefit, meaning power performance area of the chip. Your power become low, performance become better, area becomes small. So day by day, in old day, very low number of transistor, very high size. But now, so I'll get to that. So large scale integration of transistor improves the design quality in 3 different way or 4 way. Because of large scale of integration of transistor, you are able to put more and more function and features in the same chip. Chip become faster. It performance is high now. It uses low power, and its area becomes small. So all of this is possible because of your large level integration of transistor. So many transistor you put into one chip, now you are able to get all those benefit year after year. Also, because of the large integration, it reduces your manufacturing cost. When you build the chip in a fab, it has a cost. So if you can make more chip, I'll show you in a later part, in the fabrication part, how more chip can be built on a single wafer. That is a term. I'll come into that. So now the last part of this slide is the Apple's latest smartphone chip, M1 Ultra. How many transistors? 140 billion. You see how integration is happening. One single chip, you are now not only million, now you have billions of transistors. Intel's Core i9 microprocessor, which is 13th generation, it has 26 billion transistors. So all of this was possible because of the VLSI technology. You put more and more and more transistor, you add more features, more popular. Another example I would like to mention here is that the pocket calculator or even the USB-C charger has more computing speed than the best computer used to send astronaut to the moon. In 1969, right? Apollo 11 was the astronaut, the mission. So iPhone now has over 100,000 times more processing speed or power, you can say, than the Apollo 11 computer in the moon mission. Think of it. 100,000 more speed, power. So that all was possible because of this VLSI technology. Because more transistor, more features, it become faster, low power. Okay, so there's the VLSI technology. I will move into next slide. So there is a trend of I talked about transistor integration into same chip, right? So there is a trend. So this is the trend. It moves. If you see the transistor count in the y-axis and the time in the x-axis, 1970 all the way to 2000. What do you see? You see the name of a chip, and then a linear curve means number of transistors is increasing over the time. So that was the linear trend. Actually, this is exponential growth, because in the left side, your transistor is increasing logarithmically, 1000, 10 cube, and then 10 to the power 4, 10 to the power 5, 10 to the power 6, like this, right? So now this transistor trend, based on this observation, one person named Moore, he gave a law. What is the Moore's law? He says that, in 1965, Gordon Moore, he is the co-founder of Intel. He says that the number of transistors that can be integrated on a single chip will double every 2 years, or later on he said every 18 months. That means that transistor count will be double in same chip in within 1.5 hour, half year. So as you can see in the graph, that over time, 1970 to 2010, all the microprocessor name 404 and all the Pentium 4, right? So transistor count increases just like the prediction he made. So his prediction that transistor count will be like this through like this scale exactly matches. So this his bold prediction became the golden rule for electronic industry and a springboard for innovation. His bold prediction set the pace for semiconductor technology innovation for decades and is still going on. Also, the company Intel, through investment in technology and manufacturing, has made this Moore's law still a reality. It did not die, still it is going on. The transistor count is increasing on the same chip, and the increasing rate is as Moore was predicting. Okay, so world's first microprocessor 4004, right? As you see in the bottom, it has a transistor of 2300, and then later on 8008 it has a transistor of 6000, and in 2010 Intel Core processor had transistor 560 million. So it is exactly following what he predicted, Moore predicted. Okay, so his name was very famous in the chip design industry, Moore's law. Okay, I move into the next slide. This slide is talks about process technology. You will hear this term, process technology or process technology node. What does it mean? When we hear the process technology node of 90 nanometer or some nanometer, this is basically telling the transistor size, physical size of the transistor. Actually, the length of the transistor. If you remember in some previous slide, I show you the length, right? So that length, okay, of the transistor is indicated by this process technology node. If transistor length is 90 nanometer, we call 90 nanometer process technology node. If transistor gate length is like 10 nanometer, we call 10 nanometer process technology node. People will ask, what nanometer you are designing your chip now? Where is TSMC now? Is TSMC doing 5 nanometer chip? Is Intel or AMD or some other companies developing chip with 7 nanometer? So this term in chip industry will be used to indicate that what is your transistor gate length. So transistors are being developed by the research and R&D house. They continue to do research on the transistor. They try to make the length smaller and smaller so that transistor size becomes small, and then you can put more transistor into the same chip. So in the left hand side, you see there are some terminology. Micron technology. That means if your transistor gate length is 1 micron, micron technology. Submicron, less than 1 micron. Deep submicron technology means from 0.35 micron to 1.18 micron. Ultra deep submicron technology, and then nanometer technology. These all are naming convention or nomenclature of the transistor gate length, and that's what we use to tell the process technology. Okay, the smaller the process node, the more transistor can fit into a same chip. A 7 nanometer process node can fit about 4 times more transistor than a 28 nanometer process node on the same chip. Okay. So by the way, recently this description of the technology node by the nm or nanometer, the industry is trying to not use this anymore. They will say 7, the 7. They will not say nanometer because they decided to go with that kind of nomenclature. At least Intel don't add nm anymore with their process technology node naming. Okay. Moving to next slide. This is an example of process technology node. This example is from the Intel. As you can see, in 2000, their process technology node was 90 nanometer. That means what about microprocessor they were designing? They were designing using the 90 nanometer transistor, gate length transistor, and then they are developing smaller transistor 65 nanometer, 45 nanometer. That's how they give name, generation, first generation, second generation, third generation. They give name of the generation based on when they move from one technology node to another technology node. All the way to, you see, 10 nanometer node. After that, Intel decided not to use NM with their node anymore. So Intel 7. What is if anybody asks what chips Intel is designing, Intel will say we are using Intel 7 technology. They will not say Intel 7 nanometer. Intel 4 technology node, Intel 3, and then now they move into angstrom era. So transistors become more and more smaller. So from the nanometer now, 20A means 1 angstrom means 1/10 billion of a meter. Think of it. 1 micron means 1 millionth of a meter, right? 1 part of a million. 1 nanometer means 1 part 1 billion of a billion. 1 nanometer. If you have a billion and it take 1 part, that is 1 nanometer. Now angstrom is like 1/10 of a billion. So it's very, very small. So this slide is just for an example, where the industry is heading, at least Intel is heading through the process technology node. So transistor is so tiny, so much transistor can be combined into a single chip. Right? Okay, so I'm coming back to after this discussion, right? You learn about transistor, process technology node, Moore's law, and all other things. Now I'm coming back to those chip design cycle again. So as you remember, in the left-hand side, I'll talk a little bit more about the design cycle again. So at very first you have idea, right? And then in the spec number 2 is this one. This box you see, this is the spec. Spec will tell you. Okay, I'll go to the next slide basically. Okay, this is best. So in the specs section, what you do, you just tell what your chip does. What is the input output of the chip? What voltage it will operate on? What kind of, how much power it will consume? So those high level spec you write out about your chip. Let's say you want to bring a calculator into the market. Calculator is your chip. So now you are saying, okay, at what voltage it will operate, how much power it will consume, now how many input and output pin I will have. Those kind of thing will be in the spec. After your spec is developed and it was accepted by your company, then you invite the architecture and RTL engineer to write code, just like in the software area, people write code. Now in this second part, your chip will be in a code format, high level functional description of the chip using hardware description language, we call HDL. So we have two commonly HDL for chip design, two hardware description languages we have. One is called Verilog, another is called BHDL. So microarchitect and RTL engineer will write out the hardware description of the chip in this second phase. In the third phase, logic design phase, what will happen? Those code we call RTL code, those code will be converted into a logic gate. Remember I showed you the logic gate? You see in the left side, this is a logic gate. So now your chip is in the logic gate format. It was in spec, then you write architecture and hardware description, you have a code here. Then in third, your code is being converted into the logic gate. There is an industry tool that converted. The electronic design automation industry has a tool to convert this RTL code into gate. Synopsys, Cadence, Mentor Graphics, many other companies in the industry who develop those tools, and the chip design company bring those tools, or the university use those tools to convert your RTL code into logic level. And in this level, you also decide which process technology node you want to use for your chip. Is it 10 nanometer or 90 nanometer? So logic designer, in this stage, you pick your technology node. Okay, and then what? And the physical design is, it is converting physical representation, real physical representation happening here. That means you are using in this logic design, you are just saying in a logic level, let's say this gate will connect to that gate, right? But in physical representation, you really put a wire, metal wire, to connect. So all the physical connectivity with the real metal wire will happen here in this physical design. That's why it's called physical. That means you are putting your gate, transistor, and all the metal layer and connecting all the input and output. Because your chip may have, your chip may have 500K gate, right? So all of this gate has to be connected with metal layer. So in the physical design, you put real metal layer here, okay? And then when you have a physical design, then you start doing all kind of verification. That means is it functionally correct? Is the chip does what you expect it to do, right? And is there any other violation? So you fix all the violation, you run verification, and then when you are happy, then you are having a design as a layout database. So up until now, your design phase is done from your computer. Now what you will do, you will send this layout into fabrication, or in short we call fab, then it will be a chip. Okay, so then you are moving into fabrication from the designer hand to fabrication. And when it happens, chips happen in the fabrication, lot of steps happen. We have a uh, talks on this part. Our presenter will give you a talk on this part, how fabrication happen. And at the last part, you do package of your chips so that it is a nice, nice shift package chip. So that is your VLSI chip design cycle. You have an idea, you write a specification, and then your micro architecture and RTL engineer comes and they write the code of your idea based on the spec. And then logic design engineers, a set of engineers come and they convert your code into the logic gate, and then you convert the logic gate into the real physical metal layer connectivity, and then you verify your design and make sure everything is correct, no violation, nothing. There are a lot of process rules. Before you go into fab, there are a lot of process rules. Those process rules need to be cleaned up, and then you are done your design phase in the computer. Now give it to the fabrication. Okay. So I think I was trying to give you a flavor how design cycle happen. Including packaging and testing, we call it design and manufacturing. But if you do not add fabrication and packaging part, then you can say design part. From spec to design verification is a design part. And if you include everything, then you can say manufacturing part also added by adding these two steps. Okay. I think enough of here, moving into the semiconductor fabrication. So as you see that I discovered up to this, and this fabrication part will be presented by our another presenter, Ashfaq Ansari. Ashfaq Ansari, are you ready?
Yes. Can you hear me?
All right. Yes, yeah. Okay. Floor is yours. Go ahead.
Thank you, Brother Manzoor, making a good presentation on the chip design. Now, once actually Brother Manzoor makes a chip design, that it brings to our fab so that we can make the chip, the wafer out of it, and the ultimate semiconductor chip. So you hear the chip, and as Brother Manzoor mentioned, each chip is actually set of electronic circuits on a small flat piece of silicon, right? And in a chip, we have a billions of transistors. And each transistor, as Brother Manzoor mentioned, is kind of a high-end transistor nowadays, about 7 to 10 nanometer, and we're developing 5 and 3 nanometer. So you can think about the smallest size of the transistor. And if you compare to that size with a human blood cell, which is about 7,000 nanometer, right? 1,000 times actually more bigger than a transistor. And if you talk about COVID virus, which is about 40 nanometer, right? So think about the smaller scale we have to work inside the fab to make this chip. So, and because it's so tiny, it has to be developed or fabricated in a clean room. And in clean room is if you think about clean room when we think about a clean space, probably the cleanest space we can think of is a hospital, right? And the cleanest space of the hospital is actually the operation theater. But a clean room is actually 1,000 times actually cleaner than a operation theater, right? High-end operation theater. So because a tiny dust of particle will deposit on a chip, on a transistor, and create a resistance, right? When it creates resistance, takes a lot of power to work on your mobile phone, on your laptop. You don't like it, right? You want everything fast, fast, fast. You want upload photo in Facebook, Instagram, you want it right away, right? So you don't want to lose. We want less power consumption, less battery consumption, and most better output. So that's why we are adding a lot of transistor, and we try to eliminate any kind of defect in the clean room. So let's talk about the fabrication step, what we do in the clean room, right? So overall, if you think about our fab structure, we create wafer, right? And then we create a circuit on the wafer surface. And then when wafer is developed, the chip is developed, we send for packaging, which is also a very important steps. So there are actually 7 to 8 key chip fabrication steps in the fab. So let me give you a quick overview, right? And my daughter always asks me actually what you actually do in the fab, right? So I always tell her, right, hey, we make pizza in the fab, right? So how we make pizza in the fab? So if you think about pizza, right, it's made out of dough, right? And that dough is a raw material for us. It's actually we call it ingot. Ingot actually made of actually from sand. When you actually put the sand in a high temperature, it becomes liquid, then it crystallizes, and that becomes an ingot. And when we bring this ingot in a fab, we cut this ingot, right? And what we got from there, that we call wafer. And that wafer is the building block of the semiconductor. And you have a wafer, now we have to prepare it, right? Like pizza, right? You have to clean it, prepare the surface, right? So now this is you see the ingot, right? We are cutting. And then in this case, actually, we actually clean it, polish it, and oxidize it and oxidize with the silicon dioxide layer, right? Why do you oxidize? So think about iron, right? If you have an iron, right, you left outside, it will cause rusting, right? So it will get corroded. So what we do for iron, we oxidize the iron so it does not get corrosion. Similarly, for semiconductor wafer, we actually produce the silicon dioxide so it prevents the corrosion. At the same time, it produces an insulating layer on the wafer so that there is a very, very small leakage of current. Now you have the surface, right? Now you need cheese and sauce, right, to make it pizza delicious. What cheese and sauce for us is actually the photoresist chemical. So we add photoresist chemical to this wafer and expose to the light, right? And also we put the design blueprint that Brother Manzoor has and his team has made, right? Put on the wafer on the wafer surface, and with this photoresist material, we imprint that design circuit, right, on the wafer surface. So once actually this is done, and this step called, because it's photo, right? And we call lithography, we call photolithography steps. Now you made this photolithography step, you have the wafer, but you have a lot of unnecessary sauce and cheese in there, right? You have to remove it. This process we call etching process, right? And we actually remove all the unnecessary stuff from the wafer. And when you use chemical to uh, remove these unnecessary chemicals, we call it weightage. When you use gas, we call it dryage. Now weightage is dry is done, and this we do photolithography and etching process each every step by step, right? Like a deep dish pizza, and these layers actually separate by thin film, right? We call it actually thin film. And from there, to give a specific material to this thin film, we add some a specific material. we call it thin film deposition process. Then we add conductive properties, right, to this wafer surface. And we add some, and we call this ion implementation. And then we add circuit to this one through some metal wiring. So this is our metal wiring process. So that's overall what we do in the fab. There are a lot of more deep discussion available for those. Probably we can cover in future. But I'd like to give you a quick video, right, where you can see what we actually do inside the fab, how chips are being made. So, Brother Manzoor, can you run the video, please? Yes. Probably take out of presentation mode. Yeah, control, click.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that impact nearly every facet of modern life. Intel keeps powering the world. At the same time, we're powered by you, the makers, the dreamers, the doers, the people who share in our history of making the world smarter, faster, and more connected.
All right. So with that, I'll reshare again our original slide. Okay. Okay, I'm resharing our original presentation slide. Okay, so it's visible now, right?
Yes.
Yeah.
Okay.
So,
So Ashfaq, go ahead.
no, thank you. So you have seen the video, and I think I will hand over to Brother Manzoor. And please hold your question for the question answer session, or put in the chat, yeah, if you have any. Thank you.
Thank you so much, Ashfaq. It was very good and interesting video. So this is what Ashfaq was explaining, right, in the video and in his explanation, is that you create a wafer, you do all of those steps in the 7, 8, 9 steps, and at the end you got a chip, right? You package chip. So semiconductor packaging, you have a chip design in the fab. At the last stage, single chip you put like this, and then it's a package chip. Why we do packaging? We want to protect the chip from damage. It also cools the chip by heat dissipation whenever it is required to cool it down. So that was the semiconductor fabrication part. We are moving into next part. So this part will be presented by another our expert, Jawadat Rahman Romel, evolution of chip processing power and performance with the hardware and software. Romel, if you are here, floor is yours.
Yeah, I hope you guys can hear me, Manjur.
Yes, we hear you.
Yeah, thank you, thank you, Manjur and Ashfaq. So we learned a lot about what is a chip, how the chips are getting smaller, etc. I will actually talk about a different angle, like what is actually driving the entire chip industry, right? What is that? Why we are making chips smaller, more powerful? What is the driving force? The main driving force of this chip industry is software, because at the end of the day, we run different type of software on top of these chips, or use these chips to do some computing power. So that is the main driving force why the chip industry is getting smaller and smaller. I wanted to give a small idea only on computer industry. We started with a mainframe to do like, let's say, a huge amount of work, right? Eventually, and it would take a big room or big space. So I put a diagram of like X scale is all the years that you can see. On Y scale, we see the volume. So we started with very high, powerful requirement to do high performance computing. So a mainframe computer, which actually holds a room, would actually do the work. Right? We would run like only like some mathematical applications on mainframe. So softwares were mostly doing mathematical things and some research related work. Then came like mini computer workstations, where we actually, because the chip industry become prominent and they could manufacture smaller chips, so we could fit the entire computational power into a workstation. So no longer we see all these mainframes are there. Yeah, definitely there are servers and mainframes, but they would actually do a little bit different things, right? Now we went from workstation and mini computer age to personal computer age, where we had like either desktop, laptop. It would do the equal amount of work, but no longer you need to go to a big room and actually do all these mathematical things. You can bring your laptop everywhere. You can do almost the same amount of work, right? Now, actually, we can see more and more, okay, we have desktop and laptop to do some specific work, but, we want to carry all the time the computing device. So then came the smartphone, right? And a smartphone can do like an enormous amount of work, right? For example, like I illustrate an example, like today an iPhone can do 100,000 times more processing power than the computer that was built for moon mission for on Apollo 11, right? So such is the power of the small iPhone or smartphone device, right? And what is actually making it possible? The underlying rationale is that because the chips are getting smaller and smaller and more powerful, and we can fit it, that is allowing us to actually make very, very small computing device. So just for on the computers angles, like I showed an example, similarly, you can see more and more, like even car industry, there are autonomous car driving, connected car, where we can have a small chip, like actually do all the control. Self-driving cars are coming. Those are actually becoming possible because chip industry is actually making more powerful, smaller form factor chips, and that can be fit into many computing devices that we can see, right? So the angle here I can tell is that more and more high-performing computing software are coming, and the hardware industry is complementing. So software and hardware industries are working neck and neck, because we need like more powerful computers, cell phones, etc. We are actually putting this requirement from the software angle to hardware industry, and hardware industry like Intel and AMD and Apple, they are actually building and more high performing chips and more processing power and lesser space. And that is actually a good ecosystem, which is actually making human actually doing competition wherever they go. Like we carry a smartphone, and even more powerful devices are coming, like Google Glass and everything. What is making it possible is all like Manjur and Ashfaq explained, like chip manufacturing, fabrication, design technology to actually embed billions and billions of transistors in a so small form factor or tiny space, and then put it into a computing device that you can carry, you can do your work, right? And then on that device you do very powerful softwares, like you do like you name everything, like mission control of moon, and today you do everything like Facebook and like connecting to people, etc. All these control devices are possible because the chip industry is actually giving more powerful things, and the software industry is able to actually develop more and more powerful software. And then everybody right now, we are actually becoming more dependent on these devices, because we want to do computation, we want to run powerful software, be it like your social media, be it like a streaming video, etc. All of these are possible because the devices are smaller, we can carry them, and the devices are powerful because of the evolution of the hardware industry. So again, like to reiterate everything, hardware and software industry are complementing each other. Requirements are coming from software, hardware industry is making it possible, and we are actually complementing each other. That because of hardware industry is like making smaller chip, now software vendors can actually develop more and more powerful software. Right? So this slide is just to tie use cases of a consumer or a user of these chips to the hardware industry. Right? Okay, let's move on the next one. So this is a very involved slide. What I'm saying is that we all know that, okay, one single chip can do a lot of work, and it is becoming more and more actually powerful, etc. But then also software industry is coming with a lot of huge requirement. We cannot actually scale all the computing power into a single thing. So we are trying to actually make it distributed. Manjur, can you minimize the thing?
Yeah, sorry.
Yeah. So today we want to actually distribute the workload across a lot of devices, right? So this comes as a distributed computation idea. It was known long time. So early days, we had mainframe computer, one large computer with lot of small chips and located on the same room. And it could do a lot of work, but it is all actually centralized into a single computer, which has like different chips, right? So now what is happening is that we are actually designing more and more chips, but then we are finding a way to connect them to do a big thing. For example, we see what NASA is doing, like, you know, they are putting some space in shuttle in the space, and then they are controlling it. How is it possible? They are doing supercomputer. They are doing cluster of computers. They are connecting through a network. So each one is doing some amount of work, and then they are connecting to a high bandwidth networks. They are sharing data among the different computers, and each computer has thousands of chips, right? So the distributed computing, cluster computing, these actually are making it possible to distribute the workload across different computing engines, right? Similarly, a concept of grid computing is coming available. What is it? That is like, you know, you have computing power in different geolocations of the world, right? Today, we see that, okay, Google is actually saying that, hey, like when you log into Google and you just like do some search, how it is happening. You are in Bangladesh, we are in America. So there are like a way that they are connecting all the computers together. So they have like some servers on Bangladesh, some server on America, and then they are kind of sharing the data, right? So this is the base of grid computing. And after grid computing, we see that, you know, we started with mainframe or distributed computing concept, then we do cluster, grid computing. Then we actually go into like the last area that we see on the right side, where industry is going, like from few years now, and the evolution has started. Like what we will see more and more is that we will actually communicate through cluster of computers in different geolocations. They are all tied together, but each one is doing some sort of computation. So on a user, you should see some web-based like interfaces, but on the back side, there are a lot of these computation devices that Manjur and Ashfaq say that how the chip, and then they are embedded into a different geolocations. Each one is doing some sort of computation, but they are connected together. And that is becoming cloud computation. In cloud computation, then you can do a enormous amount of like computation and processing, and you as a user would not know in the background how it is possible, but it is possible due to, I say that, okay, computers, high performance computers and computing devices connected all together. In future, we will be connecting not only like computers, your cell phone, any computing device to the cloud, and that is actually happening. And sooner or later, you will see this cloud computing will be expanding. Now, like in software industry, different concepts are coming, right? You know, we need some artificial intelligence capable computers who can do billions of transactions and billions of computation in a microsecond. And because of the chip industries coming with it, and we have distributed computing approach, and we know how to connect all the computing device, in future, this cloud computing will explode, right? So that's what I'm tying it together. This hardware industry is giving us enough leverage by bringing more computing prowess through small chips. The form factors are getting smaller and smaller. You can embed them into a tiny chip, and then in software industry, we are connecting all these computing devices and coming with more and more high performance, high computing, and high performance workload that we can run through this device and communicate through this device. So in future is very bright with the computer and software industry all working in conjunction, and more high performance and computing operations will be possible through the evolution of hardware and software, right? So pretty much that concludes our discussion. Back to Manjur and others, like we can actually open the floor for question and answers now. Thank you, everybody.
Thank you. Thank you, Jawad Rahman Rubel, for your talk on this. So moving into next, as far we discussed, semiconductor designing, fabrication, software and hardware, aspects of it, and then this is a slide to end product of those chips, right? You see everywhere, chips is driving your everything, laptop, computer, smartphone, cameras, astronauts, even cars, satellite, whatnot, right? So just an example slide here. Your entire life from morning to evening and night is driven by the electronic devices which is run by these chips. Okay. All right. So we are at our third segment of our presentation today, which is the career aspect in the semiconductor design and manufacturing or fabrication area. What kind of career opportunity or path we have? We'll take a look at it in this section. Okay. So first of all, the increased demand of semiconductor chips. As you know, semiconductor or chips are everywhere, right? So that means we need lot of chips. So we need lot of chip design folks, right? We need billions of chips. We need millions of chip designer and manufacturing engineering skill worker there. So because of chips everywhere, there is a huge demand for semiconductor chips all the time. Now, there is another aspect. Recently, you heard about it, like chip shortage. So that also increased the demand of your semiconductor chips and the demand of chip design worker. What happened on the chip shortage? In chip shortage in the USA triggered due to supply chain disruption happened, and also pandemic, right? So because of the corona effect, and that disrupted the supply chain of the whole industry, because chip design in one geographical location, it can be fabricated in another geographical location. Everything has to be in a good supply chain manner. So that's disrupted happened, that makes your chip shortage, and now demand is high. Just one statistic: in 1990, in the 80% of the world semiconductors were produced in the USA and Europe. Think of it. In the 90s era, 80% of the whole world semiconductor is supplied by US and Europe, and US alone was supplying like 37 to 40% semiconductor or chips. What happened today? US alone only supplied 20% of chips. Sorry, 12%. USA and Europe is supplying or producing 20% chips. So the situation got flipped. From 80, it became 20. And if you consider only USA is only producing 12% of the whole global demand. It's very low. So because of that, USA is trying hard and desperately to increase the semiconductor chip production. So the US government came up with the US Chips and Science Act. They made this bill into law. What it is, they are pumping the billions of dollars to increase the semiconductor production in the USA. So $280 billion boost. Out of $280 billion of this Chips and Science Act, $52 billion was given only to the manufacturing, fabrication, and transistor development, R&D, research and development. Think of it. So because of that USA Chips Act and Science Act, over 50 new semiconductor ecosystem projects have been announced. Think of it, it's like a 50 company. 50 new big semiconductor projects have been declared. It is coming, 50 new projects. It's like 50 new company. 31 new tech hub in all over the USA is establishing. Government is giving money, it's pumping. So now think of another 31 new, think of this as a startup company. 31 new startup companies is coming. It's only there. And then more than $200 billion in private investment in US semiconductor production is already embedded. That means the private company like Intel and many other companies, the amount of money they invested already after this Science Act is $200 billion. So why I'm telling all of this? Because to show you that what kind of demand is there for the chips and the chip designer. As the semiconductor production expands due to the CHIPS Act, job market for highly skilled manufacturing and tech professionals are getting very extremely competitive. Talented individuals with the right skills will be in high demand. Skilled workforce from all backgrounds, not only just engineers, many other subjects area will be in high demand. So that's why I'm just bringing these 2 points. Because of the chip shortage, US is trying to cover it up. It's almost they are trying to cover it up. And then because of the Chips Act, that the new law government passed, a lot of money they're pumping to get back to their earlier position. Only 12% semiconductor, they cannot rely on it. Right? They want to get more. So that is one thing I'm just putting into perspective in terms of career, right? Chip shortage is there, and USA passed a bill. Tons of money is there, and a lot of projects and a lot of things are happening. So, in the career opportunities or the paths in the semiconductor design area, right? If you area of study in the left hand side, if your area of let me bring this point again. If your area of study is any of these, think of it: electrical, computer science and engineering, software, any kind of software, mechanical or applied physics, electronics. If your area of study is in this domain, you can do any of this job in the job functions available for you in the semiconductor design area like this. Design architect, as I show you in the beginning, that there is an architect people who write the architect of the chip, right? Design engineer, lot of different design engineer. I'll show you. Design automation engineer, validation engineer, CAD tools engineer, product development engineer, we call PDE, quality and reliability engineer. There are technical marketing engineer, sales and marketing folks also needed. So if you study any of these, you can get any of this kind of job with little bit of training, and tools training and some other skills, right? Another area, if you study this, another area is open for you is EDA industry, which is electronic design automation industry. This industry makes the tool to design the chip. As I told you in the beginning, Synopsys, Cadence, Mentor Graphics, and many other companies are in the market. They develop the tool, so they also need the engineer, right, to make their tool. That tool will be used by the design engineer. So in that company, EDA company, they also hire people if you have background on this. And their job function sometimes called application engineer, we call AE, product solution engineer, IC CAD engineer, customers specialist. So they also hire a lot of people to support the design engineer with their tool. So you have two different area, in the semiconductor design company and also EDA industry will hire you if you have studied on this domain, right? So in the design engineer alone, what they do, they can write architecture of the chip, they can do RTL coding, they can do logic design. Remember I showed you the logic design, right, in the design flow graph. Physical design, circuit design, verification, all we call in one word, design engineer. But in terms of in the industry, they will be given different role to play. Some guys will write only RTL, someone will do only logic synthesis, some other set of engineers will only physical design. If I go you one level back to show you, okay, here you see physical design. So a set of engineers will run all the time physical design, logic design. A set of engineers do logic design, microarchitecture, right? That's what I'm trying to tell you there, right? All of this act done by one set of engineer. No, you can do all of this if you're expert, but in the big industry, big company, they put bucket. Say, okay, I only need you to do logic design work. I don't need you to do RTL coding or physical design. So you can be a logic design engineer, physical design engineer, things like that. Okay, moving into my next, that same slide. That's where I was. Okay, I was here, right? I was here. So now this is the semiconductor design area. You can have your career if you study any of these. Lot of jobs available only if you in the 5 different domain study. Now I'm moving into the semiconductor manufacturing area, the fabrication area. So if you want to have a job in the fabrication or fab in the manufacturing domain, you can do it if you have study in this area of study. If you have a chemical engineering, metallurgical engineering, material science, mechanical engineering, instrumentation and control engineering, automation engineering, chemistry, applied chemistry, physics, applied physics, environmental engineering, nanotechnology study. If you have background of any of these, you are very much suited to develop your career in this manufacturing and fabrication domain. So these are the name of the engineer in the fabrication and manufacturing side. We call process engineer, manufacturing engineer, packaging engineer, field service engineer, quality and reliability engineer here again, supply chain and operation engineer. This is where our Ashfaq Ansari's expertise is. This is supply chain and operation engineer, right? So this is the career you can build if you have studied in this side. You don't have to be engineer. You see the physics, chemistry, nanotechnology, environmental, this all are needed. Material science, all are needed in the manufacturing side. Okay, so in addition to your field of area, you need to have some kind of soft skill or personal qualities to be a successful engineer in that design or in the semiconductor manufacturing side. What are those? You have to have strong communication skills. Communication means it's not just talking or writing. Communication means you clearly communicate to the team or manager or boss what you are trying to do, what you wanted to do. There should not be any ambiguity in your communication. There shouldn't be any loophole. It should be precise, to the point communication. I want to do this, I am doing this, and this is written. So many often there is a confusion what you are doing and what you are saying. So that's why in the industry we always say you need to have a very good, strong communication skills. Be precise, be clear, no ambiguity on what you are communicating to other engineers, other teams, or to your boss. And definitely you need to have a good written and verbal communication as well, right? Also, you need to have a very good problem solving skill. Analytical and problem solving skill is very much valued. So you need to develop these skills or habit while you are in university or in somewhere. Right? Ability to work in a dynamic and a diverse team environment. So you need to be able to work in a team, because you cannot just work alone. There are people who is not a good team player. You have to be a good team player. In the team, it's very diverse, meaning many different mindset of people work in a team. Somebody talk in one way, another person mean the same thing in a different way. You need to be accommodating. In the big industry, diverse means not only multinational people work. Somebody from the Central America, somebody from South Asian, somebody in North America. So that's why I call diverse team. Many different nationalities work in a team in the USA. Dynamic environment means your team is doing one thing, suddenly your project fail, the corporate will change your roles and team. They will give you another team. So you need to be adaptive. Your team is dynamic. You cannot just think you work with 6 people and in that's it. You are moving with that 6 people lifelong. No, team got break up, and again another team got formed. So you have to be adaptive to the dynamic nature of the team and diverse nature of the team. You need to have a good collaboration skills.
Manjur, we are 15 minutes past. We have to wrap through and go to question and answers. Thank you.
This is the last slide. Good. Thank you, Romel. So you need to be able to prioritize your task. Prioritizing skill is very important. You may give in multiple tasks, right? And now you have to think of which one you want to do first, which one to do second, which one third. You need to be able to prioritize your own tasks and to learn it how to do it. Another thing is multitasking. Sometimes your bosses give you 2 tasks, and then after 2 days he give you another 2 tasks. So now you have 4 tasks, but he is asking those at the same time. He was asking to deliver all of those tasks at the end of the same week. So you need to be able to do multitasking. You just cannot just stick one task, finish it, and then take another task. No. So multitasking ability is very important. Self-motivation and proactiveness. Sometimes you need to be proactive. You cannot just wait for your manager to come and tell you and you work. You pick up some work and you give the work to your manager. They love it that you are proactive. You pick it up. You don't just wait for you to be ordered by the boss, right? And you need to be motivated. Sometimes people are very demoralized. Management notice it. So show your motivation, passion when you do some work. Constructive confrontation, meaning when you work, you may confront with other team member, other colleagues, but it cannot be destructive confrontation. You cannot just give up and fight and then leave the team. You cannot do that. Yes, give your constructive opinion, but move on. Mutual respect is very important, because in a team environment, whatever task you are given, whatever task they are given, and whatever role you are play or they are play, you respect each other. doesn't matter what grade, what position you are, and what low grade position another person is at. Mutual respect in the North America is very, very important. You respect each other. No belittling. Okay. Lastly, disagree but commit means sometimes you don't agree on something with your team member or with your manager, but you cannot give up. Yes, you disagree. You can say, okay, I don't agree on this decision, but I'll continue to my work. I'll give you my delivery. So that's what we call disagree but commit. Okay. So these are very soft skill and qualities, is very much needed in the corporate or industry. Okay. This slide, I'll not spend much time. This is a slide for electrical and computer science who study. What we are telling here is that in your 4 years of study, you may complete 120 credit hour or 140 credit hour, right? We are proposing that how about out of this 140 credit hour, 9 course means 27 credit hour, or if you take 8 course, 24 credit hours. If you take 24 credit hours on this course and spend all other credit hours on any other course, then you are better off. You will be able to work as a chip designer. So we are asking only 28 or 24 credit hours out of your 140 credit hours. So you can plan accordingly in your bachelor's study or undergraduate study or even in a master's study that out of all of my credit hours, all of the course that I'm taking, if I can take only this 6-8 course, you are very much fitted to work as a chip designer. So this is for electrical and computer science and software science people. Last thing is that not only this course, you also need to have programming skills. Even if you want to work in fab or manufacturing, wherever, programming skills is important. You need to have some scripting ability and also Unix, Linux knowledge and familiarity with operating system and program, right? So those who are doing all kind of engineering degree, try to have some skills on this side as well. Okay. These are some couple of company, the chip design company and also EDA company. You can work on any of these if you study on those area of study and if you have those skill set. All kind of company names are here. Intel, and then IBM, Microchip. There are company who design chip. There are company who do fabrication of the chip. There are company who doesn't design or fabricate, just develop the tool. Like Synopsys is a tool developed company, EDA, right? So Motorola, Broadcom, all are very famous chip design and manufacturing company. AMD, Cadence is a tool developer. Cadence and Synopsys, biggest EDA company. Okay, so just to give you a flavor. So with that, I think we are done with the presentation topics. Here we are opening up the Q&A session. This Q&A session will be will driven and run by our Mohidjaman Mahmood Khanna.
All right, Manjur, thank you. Thank you to all the panelists, and special thanks to Shanaz Afrosnipa for keeping quiet and enabling us to talk. Because if you guys don't know, just in case, she was part of the faculty of WIT's Computer Science and Engineering. It's amazing that she can keep quiet and keep us honest in the background. Right. So again, I'll take 30 seconds here. The whole thing about semiconductors is enabling small size and a lot of data, and data is increasing as we speak. The volume of data going across continents, the whole world, is increasing, and God did not give sole agency of talent to any particular nation or country or ethnicity. So talent exists everywhere. What I think Manjur pointed to is there's a lot of opportunity coming up. So it's important that hopefully everybody got a sense of what needs to happen so that you're able to take advantage of those opportunities. And one of the things Manjur mentioned was proactiveness. So in that spirit, there are some pre-submitted questions, but I'll first go through the questions that are submitted real time. Couple of questions. Ashfaq, can you hear me?
Yeah, I can hear you.
Okay, so a couple of quick questions that are really interesting questions. Why is the wafer manufactured in round shape? Why not in rectangular shape? You want to tackle that real quick?
I can also add comment on it if after Ashfaq says.
Sure. Or I mean, go ahead.
Ashfaq, you wanna participation, or I can add comment with you?
Yeah, you can add comment there. Yeah.
Okay. So there is nothing wrong in rectangular. It's not like hard and fast rule, but it is the industry standard came up with a circular shape, and in the circular shape you will see the die square size is the die individual chips. So it is not any hard and fast rule. Basically, I read it and I ask the same question to our technology in the industry, but industry adopt this circular shape and it's going on as a trend.
Yeah, if I may add, Manju, real quick.
Sure.
I mean, it's round shape because of the way the ingot that Ashfaq referred to, the way silicon crystal is seated, and the ingot, it goes in a circular motion. So the ingot comes out in a like a big wide rod. So that's why.
Yeah,
right.
when you actually you crystallize the sand, so when you make the ingot, right, you make the sand liquefied and make a crystallized form, right? When it comes in a cylindrical shape, right? So when you cut from the cylindrical shape, it normally come out as a circular disc where you can make the add the circuits and wafer, right?
Yeah, so, I'm sharing the slide here also.
Okay.
Yeah, you can see the
in the spirit of keeping time, because we're running short of time, but I thought the presentation was awesome. So one other question, feel free to jump in, especially the process guys. Does technology node actually refer to the channel length? I have seen some PDKs that says it's 90 nanometer tech, but minimum channel length available is 180 nanometer. Anybody wants to take it? I can take it.
Yeah, sure.
Okay, so when you talk about 90 nanometer tech or 7 nanometer tech, it's the minimum feature size. It's
minimum
like
feature, I remember the word.
Camera, right? So channel length does not equate to the tech node. All right, then technology node folks, feel free to jump in here. How would transistors fit between such small spaces as 20 angstroms? Wouldn't there be a limit to how small the nodes can be?
So I can add one comment here. Based on the research and development, they were successfully able to develop transistor with this very little channel length, and we have a test chip. It's working. It's functioning. So it is. You can give a kudos or thanks to the research and development wing of the industry, right? They were able to develop this tiny little transistor. It is functioning. Even after 20 angstrom, there is a transistor with 18 angstrom. It is also working. We have a test chip where we are doing in the company, not in the industry yet. We are making sure all the features are really working. Yes, it is amazing, but it's still working.
Also, industry is going like Intel, like they are innovating the new transistor type, right? Not the conventional two-dimensional transistor, right? They are going FinFET, and who knows, future they might invent something else, right?
Exactly. Traditional transistor structure is being changed so that this channel length will not be a limit. They will make up with a different, there is a transistor called GAA, gate all around. So transistor technology is changing. So it will not depend on channel length anymore, but still transistor will be there. Sync will be there.
The interesting thing is, like in the textbook, what we read in the college, right, or university, is still two-dimensional transistor, right? All these new innovations, I don't think those are in the textbook yet, right? So industry is moving very fast compared to the textbook lesson.
Yeah, me too. That is an excellent point, and thank you for jumping in. That I hope that addresses the question very well. Then another question, this one I would like to address because this question has come to me in the past. Somebody named Anis Rahman, he asked a very good question. The topics covered here are software and fab. Bangladesh has limited software abilities, but fab is not possible anytime soon. What is possible to make the wafers in Bangladesh with modest investment? So this is right in my wheelhouse because I run operations. So, and I have been approached by multiple people with this question. Here's my answer. Making wafers in Bangladesh would have been impossible, or at least thought of as impossible even 3 years ago. But as Manju mentioned in his presentation, the supply chain disruption during COVID woke everybody up that cost and quality are not the only things. We need geodiversity, meaning we can't be at the mercy of a single country or two countries that if they shut down shipment, we are out of chips. While chip demand is growing, we're not getting enough shipment. That makes it worse. So I think this is definitely an opportunity for Bangladesh, but it's a much bigger question than this meeting. It will require government support and a lot of capital investment. There's no such thing called cheap wafer building.
I will add one more. I will add one more aspect of this. This
Please.
question is, so one is fab, another is design, right? That doesn't need a fab, right, in the computer. So Bangladesh has a tremendous potential to tap in those design work, because a lot of US companies, they outsource the design work. Bangalore, India is a powerhouse of the outsourcing activity. So Bangladesh has a talent. It's all you need: powerful computer and Unix network, nothing else. You don't need a fab, right? You design your chip sitting in Bangladesh. All you need is some training with the EDA tools, right? And there are some good trend I see. There are some two training center in Bangladesh. BTI, BLSA Training Institute in United International University, and also Tahoe. So I see a good trend in Bangladesh in the design center, not in the fab, but in the designs. It's already there. People are working. And another aspect, last aspect, is that because of the low cost design, we have a very big potential to tap in a lot of work, because our cost will be lower than even India. So that's why I say that I have one slide on this, right? So physical design work are being outsourced from USA to low cost region around the world. BD has a greatest potential to tap in huge amount of this design work. Because why? Because of low cost, because of competitive talents, because of ability of talents pool. We have a lot of private university, and everybody is giving EE or CSC graduate or software graduate. So I think Bangladesh has a very good potential to get some design work. We need a good intention from the government, and also the tech expert like us. We are there with them. Okay.
Thank you, Manju. That is actually, I hope this helped the person and others. That's an amazing answer. Very good answer. So there's been a bunch of questions about summer internship opportunities, full-time opportunities. What do people need to get a job or internship in Intel? What do they need to develop? I thought Manju's last few slides, which we had to go over quickly, addressed those. So please go over that offline. One thing I will tell you before I let Manju and others from Intel, because the rest of those guys are from Intel, I'm not. Intel's not the only company, even though they're probably one of the most famous. So there's a lot of opportunity across the industry. But go ahead, Manju, me too, Romel, or Ashfaq, any of you want to?
I think I can address that one. Actually, you said very nice way. Intel is not the only company. There are a lot of design manufacturing company like AMD, ARM. There are few that we name as an example, but there are lots of them. The important thing to get into these companies as a summer intern is that you have to have the coursework. You don't need to do all the 8 or 9 courses that actually Manju showed us. If you have done enough of them, you have higher chances. Another way is that, hey, if you actually, you have to select which area you want to do. If you actually don't want to walk right away into design, you can come as a verification engineer, some sort of RTL knowledge with how to write verification code or whatnot. And other than taking classes, I think there was another beautiful question, is there any online courses for actually learning this? A lot of the time we ran out of our bandwidth of taking classes in the school. So yeah, there are good online classes like Udemy Academy, Udemy Academy gives good classes on RTL design, UVM design, and test bench verification, etc. So feel free to actually go through these online classes in case if you have limited opportunity in the school. But like Manju mentioned and Adan mentioned, core courses are there. You should have a good background, and you can apply to various companies like I mentioned, right? Not only Intel, right? work as a design engineer, work as a verification engineer, work as a validation engineer. Like if you have good in software, you can go in one area. If you're good in like hardware or architecture design, you can work in other areas. So yeah, tons of opportunity. Just you have to have the background and use your online resources beyond classwork. So that's it.
Yeah. So with that said, I think we are short of time. We're 1 minute over. That shouldn't stop people from asking further questions and getting follow-ups. You have the contact information for all the right people. I'll hand it over to Nipa. Just one thing I want to say again. Prepare yourself. The whole goal here is to make sure you guys get a visibility into why this is going to be a very important, critical, key field with a lot of jobs, a lot of opportunities, and talent will excel for next several decades. So with that said, Nipa, I'll hand it off to you.
Thank you. Thank you, Mitu, Manju, Kanak, Ashfaq, and Nomel for this awesome presentation. I learned a lot, and I'm sure you did too. I didn't know about that CHIP Act, so that's amazing.
Okay, yeah, huge shift.
Huge boost to this
Lot of
industry
money,
and
yep.
a lot of job opportunities. So people, if you are interested, take advantage of this and plan your career accordingly. I know that there were more questions. Unfortunately, we ran out of time, but we do have this video posted on Boetana page. So that will always be there. If you are interested to go back and look at the slides there, feel free. There is also contact information there. And I think all of these participants, like the presenters, are on LinkedIn. Feel free to reach out to them. They're also on Facebook. So to answer any question that it didn't get addressed during this meeting. I would also like to thank our two nonprofit organizations. Both are consisting of BUET alumni living in North America. This is a great initiative, and we are hoping to see more from both of these organizations in the future. And we hope that other alumni organizations will follow and collaborate together to give value back to our communities. With that, I also want to thank our audience. You have been awesome, and I really liked all the questions. I will try to address as many as we could. I hope to see you again in the future. Thank you all.
Thank you all.
Thank you very much.